I'm really thrilled to talk about this topic because one of the reasons is nobody talks about debug because it's not a sexy product to begin with. Because it's almost like an insurance. Like, can you imagine people bragging about, hey, this is the life insurance I have? Instead, usually you talk about, what wealth you have accumulated, what features, which basically is a product features. But this is the most essential stuff. I mean, coming from a DFT background, without debug, we are definitely nothing. The silicon won't work, the product won't work, right? So that's why today I want to highlight. And thanks for giving this platform to talk about it. So they say that it takes a village to raise a child, and MTIA is our child, and this is the tribe that made this to life. Apart from this, there's a whole lot of vendors that helped us to achieve this. So if I missed out anyone, apologies. So before we jump in, what we built, I want to say why we built it. So Meta is a software company. Everybody's aware of it. You use WhatsApp, Facebook, Instagram all the time, right? Why we have to build a silicon? What's the need for us to do that, right? So the summary here is there are three graphs. The first one that I want to talk about is the pink, which what it indicates is the models that we are building, how the memory footprints of each model that we have to fit into our silicon. So it is actually quarter after quarter, it is actually growing significantly. And then the yellow line is the model size overall, including the tensors, flows, and all of that. It is also growing significantly. And apart from that is the complexity of the models. So what is that model, right? So what we refer to models are deep learning recommendation models, the DLRM. They are the fundamental, that's a crux for all our family of apps, Facebook, Instagram, WhatsApp. They keep giving you the recommendations that you like, right? So so these models exist. You have GPUs that can already solve the problem. So why we need a custom silicon? Well, number one problem is as more and more users start using it, there's a capacity issue. We cannot get GPUs like everyone else. So that's one. Second, the GPUs themselves is a general purpose where everybody can use it. But we have a specific needs and we know our workloads. We want to shape up our ASIC in a way that we want, so that we can control the destiny and we can control how we would like to achieve the target, right? So these are the reasons that led to our own silicon. So this is the die shot of our silicon MTIA V2. So V1 was launched 2 years back and V2 was launched last year. And this is a die shot. So it was taped out in TSMC 5 nanometer and frequency is 1.35 gigahertz. And gate count is 2.3 billion and the 103 million flops. It may not sound big to you right now. Hey, there are much bigger size silicons that out there. What's significant in this? It was done by just a handful of people to achieve this, and a bunch of vendors supported this. And to us, it's a great achievement to see from consumption all the way taking to a silicon. So looking into the architecture overview, so the way that you can read into it is, one, you have the compute grid, what we call the collection of PEs, the 8 by 8, which is 64 PEs are put together. And then you have this memory footprint on so memory is on subsystem on all the 4 sides of the chip. And then apart from that, there are 2 main components, which is the control core on the top and the host the host interface in the bottom. So what happens is, let's say if a workload comes in from the host, which is our x86 CPU, comes to the host interface, which then dispatched to the control core. The control core prepares the job and says, okay, I got to do a matrix multiplication. It has to figure out how many PEs that is needed. And then it will say, okay, I need a 4 by 4 grid or a 2 by 2 grid, and then patches it. Once the PEs receives the job, it will go retrieve the data from the memory subsystem on all the 4 sides, and then compute the job. Once it is done, then it pushes back to the DDR. So that's a typical workflow. What I don't show here is the NOC, which connects all of them together, right? Which is we're going to see in the next slide. So the NOC is kind of there are 2 types of NOC that we use. One is the data NOC, other one is config NOC. So the data NOC, as I just explained, is the data from, getting from DDR into the PE and then process it and pushes back. And then to configure each piece or configure some of the components, when I say configure, it is our typical CSRs that are there in the CPUs or any other registers that we want to program. So we use config knock. So the config knock is the backbone for any programming. We also use that for debugging purpose as well. So any debug traffic also flows through. So in other words, we don't have a dedicated debug traffic flowing through inside the compute core, but outside of that, we have a dedicated debug lanes that are going in. Okay, now that we understood what the silicon is and what we are building, right? Now let's look at the debug infrastructure side of it. So debug, you start from the system side. You don't start from bottom up. So you start from, okay, what is the use case? Once a silicon comes from the manufacturing, we go into the lab, what are we going to do? Right? So there are three interfaces from the outside world that we talk about. One is the PCI switch, which is the functional side of it. And then we have USB and JTAG. And USB and JTAG is predominantly only for debug purpose. We don't use it for anything else. And PCI is functional and shared between debug as well. And on the other side, we have a server, which is our x86 CPU, which is going to drive the functional traffic. And then there's a USB hub that's talked to the USB and the JTAG side of it. So what do we do on the functional debugging side? So the first one is, as soon as you have the silicon, you're going to download the HBIN file and start executing it from the CPU context RAM. So the first thing is the first fetch, right? The CPU fetches the first instruction, start executing it. I want to know if things are going right there. Or if it is not, then I would like to know why it is not. And second is there is run control, which is, as a developer, I need an ability to halt, step through to figure out where the program is getting stuck or where the program is taking the longest to execute. Right? Apart from that, I want to poke the registers to figure out what's going on. And then there are events, cross triggers, meaning there's one subsystem talking to another one. I would like to know what is causing the problem, right? I mean, there are bus analysis, there's a whole bunch of requirements, right? Most importantly, so this is how we said, hey, this is my requirement on the functional debug side. How do we go about it? Now, also, we had a manufacturing debug side. Because again, we are talking about in the lab, not in the ATE. Because in the lab, ATE test is already done, packaged, and we got the silicon back in our lab, and we are testing it, how it is doing. So on the lab side, so manufacturing side, we want to do scan dump, and we want to do in-system, MBIST, and ADPG. So one of the reasons why I'm here today is because we collaborated closely with Siemens to achieve this on the functional debugging and also manufacturing debugging. So I'm really happy, I'm excited actually to talk about it because there's not many forums we can disclose this, right? So one is, the product is called Embedded Analytics. And what they offer is a bunch of Legos, right? So let's say that, as engineers, we say we've seen a Lego. We can put together the way we can build a car, we can build a train, and whatever we want. So that's how this solution was offered to us. So you have a requirement, and you have a bunch of Legos, and you can put together. And it is not just a simple hardware solution. It is a full system solution, meaning it also comes with the software, and you can exactly use it however you want it. You want to run it in the host, and you can do that. If you want to do it in an embedded control, meaning if you want to run it within the device and the embedded program, you can also do that way. So it is nicely gelled for our requirement. So if you look at it, right, so they have monitors, which means I can monitor any internal buses of this chip, right? And you also have a DMA, which can help you to move the data from inside the chip to the outside to find out what's going on. And then you have the communication devices, which is USB, JTAG, and ASIC communicator, which is kind of the PCI way, right? You can pull the data out. On the software side, I think it's a bit complex to explain within the single slide, but in a nutshell, right, it helps you to pull the data from the silicon to the outside world. And as hardware engineers, we don't have to deal with what's going on there, right? So they made it really simple. So let's walk through a simple, okay, you said it's a Lego piece, how difficult or easy it is to put together. So this example I would like to walk you through. So this is a CPU architecture, the control core that I just walked through, right? And it has a quad-core RISC-V CPU, and there's an 8 MB of L2, and there are 4 cores that talk to each other, and then there's a 4 MB of context SRAM that is sitting outside. If I am interested to do a debug subsystem for this, what I will do is, okay, what I want to need? I want to do a processor trace. And then I want to find out what is my input and output transactions are, right? Anything that's happening inside the CPU, I would like to know. Anything that the CPU dispatches, I would like to know, right? So what we did is, okay, we just need 4 boxes. Okay, one is a CPU trace encoder. We need it because any CPU activities that's happening, I would like to collect it. And then there is a JPAM, which is responsible for the run control, as I just explained, where it can halt, step through, and figure out what is happening. And then there is bus monitor, where it is observing in all the buses that the CPU is sending out. And why we need to understand the functionality for the debugging side, right? If we don't, I'll tell you what happened, because which has happened in my first silicon, right? It's a hard learning. So you see that the bus monitors are connected to the output of CPU. But I thought, hey, I'm a smart guy. I think I can do this. I can connect it on the outside, because now I can, not only I can observe the CPU output, now I can observe all the transactions coming into the CPU subsystem, and I can observe any interrupts that are raised, any IPC that I'm getting from other CPUs, and also I can figure out all my other peripherals, what it is doing. Because it's a single entry point. It's like observing in your doorway. But what I learned hardware through my first silicon is the CPU knock. So between the previous one and this one, what we have done is just the bus monitor is moved to a different location, connected, right? The knock, right? You need to understand how the knock operates, because AXI knock something has something called an ID. So the ID is unique, responsible for each transaction that goes out. And the knock typically compresses the ID. So anything that goes out of the CPU, the same ID doesn't come out. They map internally to something else. So there was one issue that was happening inside the CPU, and we wanted to know what was causing the problem. Unfortunately, I was using on the outside of the knock, so the IDs were not clear. So that's why, so for example, there's a prefetch, there's a specific ID. And if it is a load and store, it's a specific AXI ID. Now let's say there is a load and store instruction that's having problem, you cannot really observe here, because I'm observing at the output of the knock, which ID is absolutely of no use. Still, we are able to debug and figure it out. So again, so these are that's why you need to understand the functionality well to do a better debug architecture. Now, this is the final, let's say a simplified debug architecture looks like. And what it is showing is there is a root debug, which is the doorway for a doorway entry point, which is you have this JTAG, USB, and the PCI kind of interface, and you also have a DMA SMB to move the data off this chip into for the user to read. And then you see the PE debug, which is the compute code that I explained, right, which does the DPE, SFU, any of those compute calculations. And then you have this memory subsystem debug also. So everything is observed. So the top ones are using the knock, our own custom design knock, whereas the CPU and the host, it is using the message, the debug interface that comes with it. So this is the, let's say if we take the entire chip architecture, the functional plus debug together, or the teal colors or the debug only. So the control subsystem and the root debug sitting right next to each other, and how they are interfaced. Okay, so today, apart from, now we went through functional architecture, the debug architecture. I would like to talk about a small use case. And again, there is no marketing makeup here. It's a simple engineer to engineer conversation. And this is the actual result that we got when we are debugging it. So there was a hang issue, and I want to know what is happening inside my registers. It's not like using your kind of a GUI-based debug, right? Because it's happening inside the chip. There are no eyes and ears you can figure out. There is no DB that you can load and quickly figure out, right? So using the DMA, we are able to offload what is happening inside the registers. And you can clearly, it will say that, hey, register 1, this is the address, and this is the data. And from this, we can quickly say, oh, this is where the outstanding transactions are. This is active. This is the one we got the response. This one is the one that where we couldn't get the response back. And if there is no response back, then you can go back, dig into the code, which is causing the problem. That's much easier for you to figure out what is happening, right? If this doesn't exist, your solution is not simple. One, you got to go back to scan dump out all the registers or all the flops, and then figure out at the state of hang whatever is happening. Again, that may not be the root cause. Then go back to emulation. Hopefully, they are still running the same firmware, and then ask them to recreate the problem. And provided emulation capacity is still there, because they could have moved on to other projects. So all this traditional systems is not going to help you to do modern debugging. Here is another use case with the deadlock analysis. So there was a host was issuing a read to a memory, and there was no response. Again, it went to hang state. And one of the reasons we figured out is, okay, this is the address and this is what is causing the problem. Then we figure out, okay, what is causing it? One of that is, it turns out that we have changed the address to something else, but the software was not updated, or the firmware was not updated. The moment we knew, within a matter of minutes, you can figure out what the problem is, and you can quickly resolve and move on. So I want to do a what-if analysis. What if the embedded analytics doesn't exist? What do we do? Right? In the RISC-V world, all you have is JTAG. And you know JTAG runs at 25 megahertz, at best 30 or 50, depends on what your PD team's capabilities are, and the size of the chip. So if RISC-V is, for the RISC-V subsystem, it's all ratified, it's open source, but there is not many debug solutions out there. And just to be frank, if you're using an ARM-based solution, they always provide an inherent debugging infrastructure you can actually rely on. It may be great, but again, they have their own issues, right? But if you are using RISC-V house, there is nothing out there. Everything is based on JTAG. And in JTAG also, you don't have a production-based solution. You cannot use PCI. You cannot use USB. You have to have JTAG. Now, the problem with JTAG is once you release to the production, there is no JTAG. You literally have to send someone, give them a JTAG dongle, and say, hey, go, this is a server that's failing, go attach the debugger, and then wait until I tell you. So the servers are not simple. It's not like this room. Like probably 10, 15 times bigger than this. The guy has to walk all the way through, figure out which part is failing, and then connect it, and then you can do the JTAG-based debugging. It's not easy at all. This is how you'll feel like. Actually, if you don't have any embedded analytics at all, you're in a highway lane, and the sloth is moving really slow. And this is the pace in which you can do debug, and which is what's happening in most other companies. So now that we have seen functional debug, let's look into the manufacturing defects. How do we actually do it? As I mentioned before, AI clusters are very, very complicated. One thing you can see is 70% of all the failures that we are seeing is coming from hardware. And there is good news and there is bad news. Good news, DFT engineers, you're still going to have jobs even with AI because the chips keeps failing, and nobody is going to replace them, and you're going to debug it. But bad news is we cannot train our LLMs as fast as we can. That's a problem because we're going to get constant interruptions, right? And as you can see, the GPUs are far more faulty compared to any other, like CPUs, for example. This further validates this because the clusters we are putting together are larger and larger. We are talking about, hey, Llama, we trained it with 100,000 or 250,000. We got to wait until they put a 1 million together. It's going to keep crashing every 30 minutes. And there is no way they can train it. And they're going to need all the DFT engineers best to put their effort. So what do we do if we have a failure, right? So right now, previously before we did this, right, with any other vendor-based solutions like GPUs, we figure out there is a hardware failure, ask them to ship the part to the lab. We have to recreate the failure. And if there is a vendor involved, then we will tell them, hey, you got to move it back, right? So with all of that, then what we have realized is the data center solution is not fully evolved, right? I'll give you one example. Imagine that you have a phone and it suddenly died. What do? Go replace the phone. Imagine now the phone can give you a warning that, hey, I'm probably going to be dead in 15 days. Then you're prepared to do it. And then what you do is you're going to back up the data and figure out what is happening, and then you're going to go to them and see if we can recover it. If you're still if you're not able to recover it, then you're going to replace it, right? That is exactly what happens to our data center parts as well. We don't know when it is going to crash. Suddenly it crashes. So what we did is we worked with Siemens. We came up with in-system test. Actually, this deserves a dedicated session by itself, but because of the time and we don't have room for all of this, I will probably cover in some other forum. This is a very complex architecture by itself. Thanks again for the R&D team for a close collaboration to achieve this. So what we were able to do it is, let's say whatever you did it on ATE, we can now do it on production. That's the most simplest thing, but yet it's the most complex problem to be solved. Because on the ATE, it's $1 million equipment. You do shmoo plots. You figure out which part is failing for which voltage corners, right? Now you say, hey, I'm going to take a piece of that. I'm going to achieve it in the production. And sitting in the comfort of my chair, I can push my ATPG and MBIS patterns and still test it. And I mean, 10 years back, it's an impossible task. I would have said, hey, are you kidding? There's no way we can do it, right? Maybe you can do with LBIST, and coverage at best is what, 10, 15%? But here we are talking about full coverage. If I'm having a problem in my special function units, I can run my pattern to figure out what is causing it. Let's say if one of the vendors missed, there's a test escape, and there are 100,000 parts already deployed in my data center, and I want to know what parts are failing. This is what's going to help me. I don't have to do anything. I will just update my test program, run for all these parts, whatever ones that fails, pull it out of the rack. So otherwise, imagine I've deployed 250,000 units, I have to test all of them back or replace all of them back, right? It's major disruption. And so the main features that we have done is we have closely collaborated with Siemens, where I can use my functional PCIe to push the patterns. And also, if PCIe itself is having a problem, how do I debug it? That's where the out-of-band solution comes in, which is the sideband signal, JTAG, and USB. It'll be slow, but I can still test my PCIe. So for production, I can use my USB. I can test my PCIe if controller is good. On the lab, I can still use JTAG. Okay, so I think we have covered functional debug. Then we also covered manufacturing defect-based debug. The major problem is, okay, so let's say if there is a scan dump or a failure log, you toss it to the designers, can you go debug this, right? They're going to freak out. Say, hey, it is not an FSDB, I can load it and quickly look at it. I don't have anything, right? So what we have done is, what if we have a GUI for silicon? That's what we did. So we've taken the netlist, compiled it, created a debug database. And then let's say there's a scan chain report because 103 million flops are there. And we need to map it where it is. And once you have it, you have a debug database ready. And after that, we have a debug log, which is composed of either scan dump registers, or it can be bus monitor, status monitor, or it could be register dump. Then you can do a matching algorithm where the patterns actually match. And then we figure it out, okay, these are the ones that we are able to map successfully. These are the ones we couldn't map successfully. And after that, we also do forward trace and backward trace. So people who have done DPODM algorithms in ATPG, they understand how it is. So you load the register values, and then you do forward pass, and then you do backward pass. Then you now you visualize it. You load it into the GUI. And then you'll be able to see actually each logic with their annotations on top of it. You can quickly debug where the problem is. Otherwise, imagine if one partition is failing, each partition can be 1 million flops, right? I'm going to give them a flop report with 1 million flops in it, and then they're going to load, and then another file will just have ones and zeros. They have to literally take the flop, take that value, open the netlist, and figure out where it is. Whereas with this visualizer, I can quickly see what is happening. I mean, I would have not been able to say this before 2 months, but now I can. Whatever we are doing, Siemens seems to like it, and they keep acquiring the company. Right? So I talked about Ultrasoc, they acquired it, and they became Embedded Analytics. Then we talked about Star Vision, they acquired it. Now it is part of Siemens already. So back then when we built it, we didn't know they're going to acquire. But thanks for following our lead. I think we are giving you the right cues. So, okay, you might be saying, hey, Deepak, are you saying this is the best thing after sliced bread? Definitely not. This architecture comes with a whole load of problems, right? With Meta, scaling is always an issue, same thing with debug. So the one that I talked about is one MTIA silicon. Putting in the lab, testing it's very, very easy. Now imagine the data center. So data center is like a bunch of racks, right? So you have this 12 modules per chassis. So chassis is like a tray. You can pull the tray, there is a chassis, right? And there are 3 chassis in a rack. And so on average, you're going to have 72 ASICs per rack, which is actually getting the jobs done, training the llama, giving you the recommendations, doing all of that. No, there are kernel developers who is our software developers on the other side. If I have to tell them, hey, go use this monitor to figure it out, they're going to freak out. They're going to say, I don't even know what that monitor means. You have to translate it. So what we do is we have to give them the debug architecture, and then we will say, hey, if this PE is failing, and these are the numbers that need to enable it, and we'll give you the dump, then you tell us, then we will be able to help you. So we are not, because if it's fine for 1 or 2 developers, and we are talking about 1,000+ developers. It's not even a possible problem, right? So what we anticipate, where we anticipate the future is, we want to be able to have that software to be incorporated as part of kernel itself. where they will say, hey, enable bus monitor. And it should just seamlessly push all the data out. Enable the CPU trace. And this CPU instruction is causing the longest execution. And it should seamlessly push it out. That's what we anticipate. That's a world that makes our life easy as well as kernel developers' life easy. That's where I see the next evolution of how the debug infrastructure will be. So rather than calling, I mean, this is after talking to a lot of these kernel developers, we came to know that they don't look at functional debug, manufacturing debug separately. To them, silicon is a silicon. They don't care if it is what's problem, right? So they're saying that, again, it's the same analogy that I mentioned before, like before your phone crashes, you want to know. Same thing on the data center. We want to know before our silicon crashes. So what we have done is, in the hardware level, we have added few stuff. One is PVT monitoring. Almost every silicon has it, but they don't use to the best for their, for the purpose. So it will tell how the environmental conditions are. Let's say if I'm doing over voltage or over power, right? Or if there is any marginality issues on the part, right? Those are the monitors that constantly tells me. And then you have this design monitors, which what we just, on the structural side, if there is structure-wise, everything is good, right? And we also have functional debug, which is just, embedded analytics. And then you have this in-system test. Combination of all of that actually helps us to achieve our goal, right? And then we have this whole suite software that's sitting in the hardware abstraction layer, get all the data, pushes up to the apps layer. So what we have is, when things are running, what happens is, okay, before it crashes, it notifies us. That's one. Second, when we have a large training jobs that runs for probably weeks and months, we enable all the in-system tests first, and then see how the part doing. If it's AL and healthy, then you kickstart the process. So at least I know, because the most painful task is you train it for 30 days, and then suddenly it crashes, and we don't want to deal with it, right? We want to know before. That's what all this test enables us to do. And even if it fails, we want to make sure that it doesn't occur again and again. So that's why those functional monitors are also there. That will tell us, oh, it is not a manufacturing issue, it is something else. So this is what we are able to achieve. Hope you really enjoyed the presentation. Thanks a lot. We are developing quite a bit of, thank you.